Welcome back. In this video, we're going to continue our conversation about inner products by looking at some examples of how inner products can be used as a measurement of parallelity. Recall from the last videos, one of the most important things maybe you call them a functional aspect. The reason that we use inner products, the intuition behind them, of the inner product is to provide a measurement of parallelity. And recall, we had these three cases. If U and V are vectors in R2 or R3, really, and major hint, it could be R4, R5, R6, R7. Oh my God, isn't that exciting? Goes any size as you want. You'll talk more about that in linear algebra. If you want to see that, I highly encourage you to take that class. So if we have vectors in R2 or R3, then the inner product, we hope, produces two cases. Oh, I guess we need to say the following thing. If we have two vectors in some Rn space, and theta is the angle between U and V, then we have the following three cases that we're hoping for. We have case one. This is what we call the acute case, that we say that U dot V is bigger than 0 if and only if the angle is acute. And perhaps we allow the acute angle to include 0. That would mean that these are in the same direction, which means one can be written as a scalar multiple of the other. We won't allow it to include 90 because that's not an acute angle. We call the second case the right angle case. And you could call this the orthogonal case. Orthogonal is an n-dimensional version of perpendicular. Perpendicularity holds in R2. Orthogonal holds in Rn, where n is any number bigger or equal to 2. So here we say that the dot product between those two is 0 if and only if theta is exactly equal to 90 degrees. And then case 3 was what we called the obtuse case. And in this case, we said the dot product between these two is negative if and only if, this is the biconditional statement, it means these are equivalent, the angle between the two of these is between 0 and 180. And maybe in this case we allow it to be 180 because if the angle was 180, V would be equal to some scalar c times u, and that scalar would be exactly negative, just by the way that works out. So the whole idea of the dot product was we wanted to construct this. In the last video, we actually saw a component definition of the dot product. We're going to confirm that that component definition has these properties for a select few vectors in R2. That doesn't actually prove that the general inner product satisfies these. However, it should help us start building intuition on how this behaves. Let's take a look at our first example, which is an example of case 1. I encourage those of you that are watching along at home to copy this diagram down in your notes, make it look real beautiful. I'm cheating a little bit here. because I want to make it look beautiful for you. This took me about 20 minutes to produce the first time I produced it in Mathematica. So I don't think it's going to take you that long to do it in your own notes. Okay, so the whole idea here is we want to look at the case that that theta is between 0 and 90. Here we have two vectors u and v, which is 4, 1 and 3, 4. Visually, we confirm that the angle between the two of these is less than 90 but greater than 0. Let's go ahead and take the dot product and see whether or not the dot product should be positive. So u dot v, we're going to use the component definition, and I'm going to really be obnoxious and write out all of my steps just because this is the first time I've done it. I tend to do that often in my math career, write out all the steps, just because it doesn't really take that long and it can make a huge difference later. Okay, we see that indeed for an angle that's between 0 and 90, we get a positive number. That doesn't prove it's true in general, but it does start giving us an intuition about how this should behave. Let's take a look at case 2, where we're going to find the dot product between two vectors that are orthogonal. It takes a few seconds. It should take a few seconds for you to confirm that if I have a vector u, which is -4, 4, and a vector v, which is -4, -4, that these are actually orthogonal, that the angle between the two of these is 90 degrees. One way to look at this is just recognize this as a pi over 4 shift of the two unit vectors along the axis. Do you see it? That's called an orthogonal transformation. We notice that if this is indeed orthogonal, which we visually confirm that it is, that the dot product between the two of these things should be 0. Let's take a look. When I take the dot product here, I'm going to multiply -4 times -4, and I'm going to add that to 4 times -4. Here we get the same component. This is positive 16 minus 16, and of course we get 0, and we see that an angle of 90 degrees corresponds to an output of the dot product of 0 under this component definition. Where remember, the components, we take the first component of the first vector, multiply by the first component of the second vector, and then add that to the product of the second component of the first vector times the second component of the second vector. Let's take a look at our third case, a set of vectors that satisfy our third case. Again, I'm hoping that you're copying these examples down. So we have a vector v that is -2, 1, and a vector u that is 6, 1. Let's take a look at the angle between the two of them. Of course, we hope to call that angle theta. It looks like theta is bigger than 90 degrees. Later on in this lesson, we'll actually be able to confirm that with a mathematical argument that we also prove for ourselves. Here we go. We take the dot product between these two vectors. The component definition of the dot product requires that I multiply the first two components together, and I add that to the product of the second two components. Here I get -12 plus 1, which is, of course, -11, and we see this is less than 0, corresponding to an obtuse angle. This doesn't prove that the component definition of the dot product satisfies the claim that we made about the three cases. What it does for us is give us some base cases to start building intuition. In the next video, we're going to look at some algebraic properties that come from the component definition of the dot product. I'll see you in the next video.